what is a heap? And what can you do with it, and why is it important? Well, a heap is a type of data structure, and it's got 3 different operations, and sometimes more, and you can find the element with the minimum priority, you can delete from it, and you can insert into the heap. In fact, what makes heaps so popular is that they're almost synonymous with these things called priority queues. And priority queues, well, you can just think about these operations here like you would in a traditional FIFO first in, first out queue, except with priority, when you do these operations, you're going to get the most important thing first when you peak and when you pop. Alright? So that means if thing 1 and thing 2 have different priorities, well, no matter which order they get pushed in, as long as they're still in the queue when we peak or we pop, we get the thing with higher priority. Alright, so why use a heap instead of something like an array? Well, let's say you had this number 4 right here, right, that you want to insert. Well, you might be able to see that this is sorted data, right? What does that mean? You can probably binary search for the correct position. However, if you insert something into an array, you got to shift all the elements right back. And so this is actually an O(n) operation. So not that efficient if you want to put in elements. It's going to cost a lot of time. You might also think, well, what about a linked list? Well, the problem with the linked list is that although it's great for inserts, right, you still have to find where to put 4 into this linked list. So that's where the heap comes in. We're going to see how we can support these operations, specifically using a sequence heap. A sequence heap is different than your typical heap. It is not going to be tree-based like this. We're actually going to go and see something a little bit different. Alright, this is a sequence heap, and you can see that it's actually comprised of sorted linked lists that are actually in size related by a ratio. And this ratio is what I call this rank factor, and here it's 4. So each linked list, each successive one, is going to be 4 times the capacity of the previous one. It doesn't mean that it's always 4 elements. Sometimes it could be less, sometimes you delete from it, but overall, the capacity doesn't change. Alright, here we see the max rank is 1, right? This is denoted by these segments here, labeled S0 and S1, and if we get to it, S2. Okay, so here's how sequence heap works. You ready? First off, let's insert the element 8. What's going to happen here is that we're going to create a new kind of linked list with just the element 8, and we're going to start merging, right, with the first ranked linked list. And when we merge those, we use that typical two-way merge algorithm, and that's actually going to allow us to get this 3 and 8 right here in sorted order. Alright, unfortunately, the first segment is over capacity, so now we merge into the next rank. How do we do that? We use the same two-way merge strategy, and we have 3, 7, 8, 9, 9, and 11. Right? But now, S1 is also over capacity, and when that's true, we merge into the next rank. Turns out, the next rank is null, so what happens is that we bump up our max rank, and you can treat this like merging with an empty list. Now all our elements are on the second, the linked list at rank 2. Next, let's insert an element 5. Well, create a new linked list with just the element 5, and we merge into the 0th rank. Boom! And we're done. We're within capacity. Now let's insert this 1. Well, it's the same story as before. Create a new linked list with 1, and then we see this 5 at rank 0. We merge them using that two-way merge strategy. Boom! We got 1, 5. But now we're over capacity, so what happens? We're going to merge with S1 right here. Boom. And we're within capacity, so we stop right there. The next operation comes in. It's a insert again. And it's the same story, and I've sped it up for you. Right? Now what happens when we do a find min? Well, if you've noticed, we only have sorted linked lists. So out of all our sorted linked lists, we actually only need to look at 3 of them. And boom, we just look at the min between 2, 1, and 3, the heads of our 3 linked lists. That answer is 1. Because it's just a find operation, we don't change the heap at all. Next up, what happens if we delete? Well, it's much the same story. We can look for the smallest element that exists between our linked lists, and it's going to be just this 1, as we saw before. With delete, we actually mutate. So, boom, we just truncate that one, and we're left with 2, 5, and 3 as the heads of our linked lists, and we can return the smallest element here. Next up, what if we insert a negative 1? What happens is that we have negative 1 and 2, we have a capacity, merge in the next rank. Getting familiar? It's good. Alright, within capacity, we're done merging. And that's basically how sequence heap works. If you've noticed with the find min and the delete, it's actually possible to make a find min an over 1 operation. All you have to do is remember what the minimum was. You can do that by tracking the inserts and the deletes as well. If you wanted a O of 1, find min. All right, but let's head back to looking at what is the actual time complexity of this scheme. Let's look at time complexity. We got 3 operations, so let's go through each one. First up, we got delete. And if you notice that in this diagram here, each sequence is going to be of a size that's a factor greater. So we're actually talking about taking exponents and powers. You can see that this is actually O of log n because there must be, at most, the ceiling of log n many linked lists. And let me give you an example. Let's say there's going to be 64 elements. All right, 4 to the third equals 64, and you do a basic logarithm math, and you get 3, right? Should be your max rank. So what about the number 75, for example? Or let's say 86, right? If you look at the diagram here, 1 plus 4 plus 16 plus 64, well, that actually equals 85, right? To have the 86th element, we would need to create the actual 4th rank. But that's going to help keep enough elements to allow us to store 256 many more. It's important that when looking at this analysis, I'm actually counting all elements that have ever been pushed onto the heap as n. Okay? Ooh, next up, we got peak. This one's going to be log n, same as above, because we're just going to be looking over log n many heads of linked lists. Next, we got insert, and actually this one's going to be a bit more complicated. To do an analysis of insert over all insertions, well, that's what's called an annotized analysis. To begin, let's look at this sequence heap. Alright, let's say it actually happens to be full without loss of generality. Now, there's n elements inside this entire thing, and notice that on the last linked list right here, we can count how many operations it took to get here. Remember from a sequence heap that the amount of merges that we do ends up being bounded by b, because we might need to merge up to b times into the next linked list from the previous one in order to fill it all up. Okay? So if that's true, then we can start looking at that last one as having traveled log n levels, right? So this is the amount of times it's had to cross from one rank to the next, right? And in order to get to the max rank, well, it's had to go log n times, all right? And the amount of comparisons that you do in each rank happens to be b, right? With the last rank being of no exception to that. Now, finally, we look at how much time the comparison took in order to get here for each of the elements. Well, that time is actually going to be bounded by O of S of max minus 1 plus S of max, specifically the sizes of those two lists. In fact, we can just upper bound this very easily, and we'll just say that's n. All right? So right now what we have here is log of n times b times n. So that's the amount of time that it took, right, in order for all these elements here to get to this last rank. All right? This is the time complexity only for these elements at the last rank. Now let's count for all the other elements. I actually find that to be difficult, so instead what I'll do is I'm going to note that actually the elements in the last linked list make up over half of all the elements. And this is true so long as b is greater or equal to 2. So for example, if your b was 4, well, you can see that actually this 4 to the third, or 64, is actually much bigger than half of all the elements that exist in the sequence heap. So what argument can we make over all these elements is simply by the fact that it must be bounded, right? It must be bounded by log of n times b times n, because if most of the elements have made it to this last sequence right here, and less than half the elements have not, we can write an upper bound as 2 times log n times b times n. If we were to simplify this in terms of n, this would be n log n time complexity for all insertions. Alright, so that's amortized. And now what you can do is, with this knowledge, well, you can take n log n, and just with some very rough mathematics, if this is the time it takes to insert all elements, right, but the amount of elements is n, then you can say that the average case is actually going to be log of n time per insertion, right? And it's very important to note that this is amortized. Next, let's look at the time complexity of a single insert. This is amortized, but what's the best and worst case? Well, we know that for the best case, it must actually be O of 1. And why is that? Well, when there's nothing at the 0th rank, you just pop something new in here, and boom, you're done. Easy. Now, let's think about the worst case. Well, what is the worst case? Well, the sequence heap has got to be full in order for the worst case to happen. This is going to maximize the amount of comparisons that we're going to make. All right. So in the worst case, we got b. Well, I'm going to say this is the amount of elements. This is our base, right? And this is the exponent. B sub b to the 0th, b to the 1st, b to the 2nd, all the way to b to the max minus 1 and b to the max, right? Just our generic sequence heap. Okay. So if we merge something new in, right? Let's say a new element comes in, we're going to have to do cascading merges. And this might look bad at first, but I'll show you it's not actually that bad. All right, so if you look at here, what are the cascading merges going to look like and how many comparisons is that going to be? Well, you have b0 plus b plus 1, right? Because for two elements, you really only need one comparison, right? And once you have these two elements and you have these four elements, well, what that's going to be is when we do the cascading merge, you're going to take the amount of elements that you have now previously, and you're going to look at the amount of elements that you're currently merging. All right? So hopefully that makes sense, because this is the amount of elements now, right? Now that you have two, and you now merge with four at the second rank, right? And so on and so forth. So that eventually you have what is on in these parens, the size of the left list, right? And you also have now on the second term, the second list that's being merged. So this would be the last term, right? Because this would be max rank right here, right? And this would, let's say, be max minus 1. This is 1, and this is 0, right? And let's pretend that there's some other linked lists in between here. So if you look at here, you can actually start grouping like terms. So actually you have b sub 0, I mean b to the 0th, and how many times are you going to have that? We're actually going to have that max plus 1 times. And how many times does b1 appear? Well, b to the 1st appears max amount of times, right? And so you keep going onwards, and you see something rather interesting. This is actually an upper bound, right? This is actually upper bounded by n. And in fact, how many elements is b to the max minus 1? Well, it is actually going to be n divided by b, isn't it? And you can see that actually what we're going to end up having is b squared times log of n minus 1 about. You can see actually that let's say we reverse the terms, right? So let's say we have b max over here plus b max minus 1 times 2 plus b max minus 2 times 3, and all the way until you get this b to the 0th, right, which is just actually the value 1, right, times max, right, plus 1. Okay, now what's interesting is that you can actually upper bound all of these elements, right? So b to the max, well, that's got to be upper bound by n, because n must be at least greater or equal to the b to the max. What about b to the max minus 1? Well, this is actually just n, but then divided by b many elements, right? Because it's geometrically progressing series, right? So this is n divided by b squared, right, times 3, and so on and so forth. And actually, you can do a little bit of arithmetic, and you can see that this is n times this series of 1 plus 2 over b plus 3 over b squared plus, all the way over whatever's on the right-hand side. I don't need to write that out because actually I know something very important about this series. And this is so that when I equals 0 all the way to infinity, and if you have on the top what is just going to be I plus 1, right? And what's on the bottom, well, it's actually going to be b to the I. This actually converges, right? Hopefully you remember that from calculus class, but the main intuition is that the denominator increases so fast compared to whatever's on the numerator that if you have an infinite amount of terms of these things, you're still bounded by a finite value. You just can't overpower how fast the bottom is moving. All right, so I'll also note that this converges, and you got to make sure that b is greater or equal to 2 for this to be true. And therefore, because this converges, it's a constant, and you have just O of n time complexity on the worst case. One last thing I'd like to mention about a sequence heap is that you can easily imagine it as a double-ended priority queue as well. How does that work? Well, the mins are all up here, but each of the ends is also a max of its list. Therefore, if you actually had a node that was able to find the thing above it, you could easily find the maximum of each of the linked lists, and the maximum of those is actually going to be the maximum of the entire heap. In order to do that, you gotta keep an extra pointer on the nodes that you use to help you maintain that heap invariant when you do the deletes. To finish, we've shown that the sequence heap can work as a priority queue, supporting insert, delete, and also find min or peak. For insert, we got amortized log n. For delete, we got log n. And for find min, we got log n, or you can make that peak O of 1. Thanks so much for your time. Like and subscribe, and have a broken dog. Good night.